Tropical forests are among the most productive ecosystems on Earth. They account for the majority of global forest carbon uptake and store over half of the world's forest carbon. Maintaining this exceptional productivity, however, requires a steady supply of essential nutrients, which are constantly lost through processes like leaching, erosion, and biomass removal. In these nutrient-demanding environments, external nutrient inputs are crucial. Traditionally, three natural sources contribute to replenishing nutrients in ecosystems: mineral weathering, biological nitrogen fixation, and atmospheric deposition. But in tropical lowland forests, where soils are deeply weathered and the landscape is relatively stable, weathering rates are typically slow. Moreover, biological nitrogen fixation in these forests is highly variable, with both high and low rates reported across sites and seasons. As a result, atmospheric deposition may represent a significant and often underestimated nutrient input in tropical forest nutrient budgets. Atmospheric deposition occurs when airborne particles and gases settle onto ecosystems, either dissolved in precipitation or deposited directly onto surfaces. These particles originate from a range of natural and human-related sources, such as sea spray, dust, fossil fuel combustion, and biomass burning, and their deposition influences nutrient cycling and forest productivity. Despite its potential importance, atmospheric nutrient deposition remains poorly quantified in tropical regions, particularly in the wet, equatorial forests of South America. There is a marked scarcity of long-term empirical data, especially in comparison to temperate regions. Yet, with ongoing increases in atmospheric nutrient emissions from global industrial and agricultural activity, this knowledge gap is becoming more critical. To better understand this process, the 2020 study by Van Langenhove et al., Atmospheric Deposition of Elements and Its Relevance for Nutrient Budgets of Tropical Forests, focused on quantifying atmospheric deposition of nutrients in a pristine tropical forest in French Guiana. Over a 15-month period, the team measured nutrient concentrations in rainfall, both in open areas and beneath the forest canopy. They also assessed nutrient cycling through litterfall, the shedding of leaves and organic material. By integrating these measurements with a canopy budget model, the researchers aimed to distinguish between nutrients delivered from the atmosphere and those redistributed within the forest canopy. This approach provides a more detailed picture of how external nutrient inputs interact with internal cycling processes, offering valuable insights into the nutrient dynamics that sustain tropical forest ecosystems. This study was carried out in the Parakou Research Station, a well-established ecological site located in the tropical lowland forests of French Guiana. This region experiences high annual rainfall, around 3,100 millimeters, and a warm, humid climate with a pronounced dry season. The forest itself is old-growth and highly biodiverse, growing on nutrient-poor, heavily weathered soils. These conditions make it an ideal location for studying how atmospheric inputs contribute to nutrient cycling. To assess the contribution of atmospheric deposition to forest nutrient budgets, the researchers designed a 15-month field campaign that measured nutrient inputs through rainfall and internal forest processes. Specifically, they focused on three main components: bulk precipitation, throughfall, and litterfall. Bulk precipitation collectors were placed in open areas to capture rain unaffected by vegetation. Throughfall collectors, on the other hand, were placed beneath the forest canopy to capture rainwater after it interacted with the foliage and branches. These samples help the researchers determine how the canopy altered the chemical composition of rainfall, either by adding nutrients through leaching or removing them via uptake. In addition, a network of litter traps was used to measure nutrient recycling through the natural shedding of leaves and other organic material. This allowed the researchers to compare external nutrient inputs from the atmosphere with internal nutrient cycling on the forest floor. To interpret the complex interactions between rainfall, canopy processes, and nutrient movement, the team applied a well-established tool called canopy budget model. This model distinguishes between nutrients that are delivered to the forest via dry deposition, fine particles, and gases that settle onto leaves, and those that result from internal canopy processes, such as nutrient exchange or leaching from plant tissues. By using sodium as a tracer, assumed to behave conservatively within the canopy, the model helped separate external deposition from internal redistribution. Together, these coordinated measurements allowed the researchers to quantify and compare atmospheric nutrient inputs with internal cycling, revealing the relative importance of deposition in sustaining this tropical ecosystem. Over the 15-month study period, the researchers recorded approximately 3,550 millimeters of rainfall in the open clearing, while throughfall beneath the forest canopy measured around 2,830 millimeters. This indicates that about 1/4 of the rainfall was intercepted by the forest canopy before reaching the ground. In terms of nutrient deposition, the atmospheric input of nitrogen compounds via precipitation was relatively high. The total deposition of dissolved nitrogen reached approximately 13 kilograms per hectare per year, with the majority in organic forms rather than as nitrate or ammonium. However, internal nitrogen recycling through litterfall was far greater, with around 82 kilograms of nitrogen per hectare per year returned to the forest floor via shed leaves and organic debris. Phosphorus inputs from atmospheric deposition were modest but still notable. Total phosphorus delivered via rainfall, including both wet and dry deposition, amounted to about 0.5 kilograms per hectare per year. This external input represented roughly 1/3 of the phosphorus returned through litterfall, suggesting that atmospheric sources may play a meaningful role in phosphorus availability in this nutrient-limited forest. Potassium presented the most striking pattern. Atmospheric deposition delivered about 14 kilograms per hectare per year, and an additional 22 kilograms per hectare per year were released through canopy leaching, where rainwater dissolves potassium directly from plant surfaces. Combined, these sources contributed over 3 times more potassium than the amount recycled through litterfall, which was approximately 11 kilograms per hectare per year. The canopy exchange model revealed that while some elements, such as nitrate and phosphorus, were taken up by the canopy, others, like potassium, were strongly leached. Overall, the findings show that atmospheric deposition, particularly for potassium and to a lesser extent phosphorus, represents a significant external nutrient source relative to internal recycling in this tropical rainforest. The findings of this study shed new light on the role of atmospheric deposition as a nutrient source for tropical forests. By integrating detailed field measurements with a canopy budget model, the researchers were able to isolate and quantify external nutrient inputs relative to internal recycling. This approach has revealed important differences in how various elements are deposited from the atmosphere and subsequently processed by the forest canopy. One of the key insights is the differentiated behavior of nitrogen, phosphorus, and potassium. While atmospheric nitrogen deposition was relatively substantial, it was still overshadowed by internal nitrogen recycling through litterfall. This suggests that in this mature tropical forest, likely rich in nitrogen, atmospheric nitrogen inputs play a secondary role in sustaining productivity. Furthermore, the forest canopy showed signs of actively taking up nitrogen compounds, indicating a capacity to retain these inputs before they reach the forest floor. In contrast, phosphorus deposition, though much smaller in absolute terms, was more consequential relative to internal cycling. Given the low phosphorus availability characteristic of many tropical forests, even modest atmospheric inputs can significantly influence nutrient dynamics. The observation that phosphorus was taken up by the canopy rather than leached aligns with the idea of a tightly conserved phosphorus economy in this ecosystem. Organisms living in the canopy, such as microbes and epiphytes, may play a key role in capturing this scarce resource. Potassium emerged as a particularly dynamic element. The high levels of leaching from plant tissues point to its mobility and abundance in canopy structures. Since the external input of potassium from atmospheric sources exceeded the amount recycled through litterfall, this element appears to rely more heavily on ongoing deposition to sustain its availability. Such findings highlight the important contribution of atmospheric inputs to potassium cycling in tropical ecosystems, an aspect often overlooked in nutrient studies. This study also underscores the importance of canopy processes. The forest canopy is not simply a passive filter for rain, but an active interface where nutrients can be absorbed, released, or transformed. Understanding these interactions is essential for accurately estimating nutrient budgets and predicting how forests respond to environmental change. At the same time, the authors acknowledge several limitations. While the use of sodium as a tracer ion is standard in canopy budget models, it may not be entirely inert, potentially introducing uncertainty in the separation of dry deposition and canopy exchange. Moreover, the study's temporal scope, 15 months, captures seasonal variation, but longer-term monitoring would be valuable to assess interannual trends. Ultimately, this research contributes vital empirical data to a region and topic where such information is critically lacking. With global changes in land use, climate, and atmospheric composition, understanding nutrient deposition in tropical forests is more urgent than ever. Studies like this help bridge the knowledge gap, providing a foundation for future work on nutrient dynamics, forest resilience, and ecosystem management in some of the world's most vital and vulnerable biomes.